Okay, so you know me, I'm Dr. Muhammad Umar Siddiqui, and inshallah we are going to study the course of, please close the door. We are going to study the course of heat and mass transfer, inshallah this semester. You already have a background of thermodynamics, okay? This course is a very important course in the sense that it's going to be a prerequisite of many courses that you will have. One of the most important courses that you will have is the renewable energy, and prerequisite of renewable energy is heat and mass transfer. You cannot take renewable energy until and unless you have actually cleared and understood the course of heat and mass transfer very well. The heat and mass transfer is actually not just for renewable energy, many other courses. It's a prerequisite of many courses. However, let me tell you, this is comparatively a difficult course. It's a heavy course. You do need to spend a lot of time on this course. Okay. What background you have is of thermodynamics, and in thermodynamics we studied many different kind of energy systems. We studied many kinds of energy systems, okay, and we studied some components within those energy systems. For example, the condenser, the evaporator, and we know that the condenser rejects heat, and we know the evaporator takes in heat. We know the boiler takes heat as an input. But how does this heat transfer taking place? Okay, this is something that we did not study there in thermodynamics. That's the detailing of the components. Okay, all these are heat exchangers. All these are, we studied some heat recovery heat exchangers as well, okay? But how does these heat exchangers made? On the paper we draw it with a box, but in reality they are more complicated than a box, okay? There are a lot of things involved in it. What's the construction? What's the sizing of the heat exchanger? What's the cost? Everything, okay? What's the pressure drop across them and everything. So these factors are very important, and these are the factors that you're going to study now in detail in this course, heat and mass transfer. Okay. So one thing about the course is that this course is applicable in every field. This course is applicable in every field. It means one thing: it will have general laws, and those general laws will be applicable in different areas. So you will have problems from the biomechanics to this renewable energies to the regular things happening in our life, okay, to the big power plant systems. So in variety of fields, this course will be implemented, okay, and the laws will be implemented. So sometimes it becomes really difficult, because you just don't need to know the laws based on which this course is defined. You also have to understand the scenario where it is being applied, okay. So it becomes a bit more complicated in that sense. First understand the scenario, then apply it, okay. So anyways, just as a beginning, this course is a bit heavy course and you need to spend some time in it, okay. The homework, I have already assigned the homework problems in the course, and the homework problems are selected as per the teachings for the contents of the course, okay. And the homework problems themselves are very heavy. Okay, so you have to spend some time over that as well. So let's continue for now. Chapter number 1, Introduction. Well, it's a misnomer here. It is introduction, but it's going to introduce all the processes of heat transfer here, okay, and in a quite detail, which presumably you should have done before, okay. But anyways, it's going to be a recap, a review of what was supposed to have been learned by you guys before. Okay, why do we study heat transfer? I don't need to answer that question. Everybody knows it. It's the most important phenomena occurring around us. Okay. Why do we study heat transfer? From the study of thermodynamics, we have learned that energy can be transferred by interactions of a system and surrounding. This is what we studied in thermodynamics. We have a system and a surrounding, and the energy interactions takes place. Okay? And these interactions are basically the work and heat interactions. Okay? However, thermodynamics deals with the end state of the process during which an interaction occurs and provides no information concerning the nature of the interaction or the time rate at which it occurs. So it just tells that, okay, that much amount of heat need to be rejected, that much amount of heat need to be supplied. But how does this supply or rejection take place, or in what amount of time? This is not basically studied in thermodynamics. This is not what you were taught in thermodynamics. So in thermodynamics, you were taught on the macro scale. Now you're going to go deep. Okay. The objective of this course is to extend the thermodynamic analysis through the study of different modes of heat transfer and development of relations to calculate heat transfer rates. So you're going to study different modes of heat transfer, and then you will develop relations to calculate the heat transfer rate. Okay? So this is what this course is all about. Now let's talk about the modes of heat transfer. Okay? You studied before the modes of heat transfer, I think, in your physics. Okay, do you remember what are the modes of heat transfer that we have? Convection, conduction, radiation. That's true. But physically, do you understand what does they mean? What does conduction means?
It's like two bodies that touch you. When they touch, they transfer it.
What about convection?
Not sure.
Convection, maybe there is no need to touch. Maybe you can.
Good. What about radiation?
You can see from waves.
From
Microwave.
Okay. Okay, let me give you the physical understanding of these modes of heat transfer. Suppose we all are molecules, and suppose this is heat. Okay. Now, I need to transfer this heat from one place to another. Okay. So I need to transfer this heat from one place to another. Okay. One way is that I stand on my position. I do not move myself, but I give it to you. You pass it to the other person, staying on your position. You pass it to the other person, then you pass it to the next, until it reaches where I want it to be reached. Now, if the heat is transferred in this manner, where the molecules don't move themselves, they interact with each other, but they don't change their position. If the heat is transferred in this sense, this is known as conduction. Is it clear? Molecules vibrate. Vibration is different. Vibration, when we say that molecule move, we mean its mean position is displaced. Vibration means on the mean position moving back and forth, but the mean position remains same. Okay? So there is no bulk motion. Okay? So, but with the vibration, what happens is that the molecules interact with each other. So the energy is transferred by the interaction of the molecules. Okay? So if the energy is transferred by this means, when the molecules vibrate, interact with each other, but do not move themselves and transfer the energy, then this kind of energy transfer is known as conduction. Okay? So that's the first mode of heat transfer, which is conduction. Okay? And it has another name. It's known as conduction, and the other name is diffusion. It's the same thing. Okay. So conduction or diffusion. That's the first phenomenon. That's the first mode of heat transfer. Okay. Then let's talk about the second mode. Now the second mode of heat transfer is that, look, I'm here and this is the energy. Now I want to transfer this energy from here to there. One way is we studied conduction, that I don't move and I transfer it taking your help. Okay? The other way is that now I don't take your help, but I have the energy and I move myself with the energy and transfer it to the position where I want it to be transferred. Now, if this is the case, then this kind of heat transfer is known as convection. In convection, the molecule move with the energy, okay, and then transfer it. So this kind of heat transfer is the second mode of heat transfer, and it is known as convection. Okay.
So can we say that the first one is the solid state, the second one?
Yeah, implicitly, but let me explain this furthermore. Okay. Now, basically, convection is this kind of heat transfer, but convection is basically a term which is composed of two words, con and vection. Right? Convection is basically composed of con and vection. Con comes from conduction, and vection come from advection. Right? So advection means the bulk motion of the molecule, but conduction means diffusion. I can move with the energy. I can move with the energy, but once I reach here, I have to interact it to transfer. Right? So it's a combination of conduction and advection. Is it clear? So that's why this is known as convection. But the conduction portion is very small. The larger portion, transfer of energy, is basically due to advection.
So the two bodies must to touch, right?
Yeah, obviously. For interaction, there has to be, for transfer of energy, there has to be an interaction. Okay? But only thing is that now the molecule move themselves and then interact where they want to transfer the energy. Is it clear? So this is convection. It's a combination of conduction and advection. Advection is the bulk motion of the fluid. Conduction is something you know, interaction, transferring energy by interaction. Okay? So that's the second mode of heat transfer. Now in the second mode of heat transfer, molecules, heat is not transferred majorly because of the interaction, but it is majorly transferred because of the bulk motion of the fluid themselves. Fluid themselves move with the energy. After that, they interact and transfer energy where they want to transfer. Okay, now we have the third mode of heat transfer. The third mode of heat transfer is that I am standing here with the energy and I want to transfer energy. Now, the first way was that I take help from you guys and interact, but don't move from my place. The second way was that I move myself. Okay. Now I don't want to move myself, and I don't want to take your help.
Yes.
Now the way is that I throw it. So if I throw it, energy is still transferred. But that kind of transfer or mode of transfer is known as radiation. So we have conduction, we have convection, we have radiation. And how do I throw energy? It's through the electromagnetic waves. So I emit electromagnetic radiation and the energy goes with it. It does not need any medium. Okay? I don't need to carry it. I don't want you to take it. It will be thrown directly. It does not need any medium to transfer. It's clear? So these are the three modes of heat transfer that you are going to study in this course. Conduction, convection, radiation. Okay? Conduction, it will be from chapter number 2 to chapter number 5. Convection, it will be from chapter number 6 to chapter number 11. Radiation, it will be chapter number 12 and 13. Okay? But this course is named Heat and Mass Transfer. So you will have the last chapter for the mass diffusion. And mass diffusion is very, very similar to the heat transfer. So we will study in reality the heat transfer and apply the same analogy for the mass transfer. Okay. So this is what this course is all about: conduction, convection, radiation. Do you understand physically what does these modes of heat transfer mean? Anybody has any question? Anything that you don't understand? Good?
Good.
Okay, so let's move ahead. Now there are certain terminologies there that we need to understand. Yes?
You said bulk motion.
Bulk motion. Bulk means mass motion or something in large quantity. Bulk means something in large quantity. Bulk of fluid, large amount of fluid. Bulk of students. Okay, bulk of lectures.
I thought the bulk is name of size.
No, bulk, B-U-L-K, it's an English word. It means kathir. Okay? now I'm learning Arabic as well. Okay. So now there are certain terminologies that we should understand, okay? And we should be able to differentiate between them. The first thing is the thermal energy. Thermal energy is the energy associated with microscopic behavior of the matter. The energy content of a matter is thermal energy. How much energy is there within something? That is the thermal energy. Okay? And it is its symbol is U, measured in joule or kilojoule per kg, like that. Okay? The second thing is the temperature. Temperature itself is nothing. It is just a tool to measure thermal energy. How can you say that thermal energy is more, or how can you say thermal energy is less? Based upon temperature. If thermal energy is more, then temperature will be high. Thermal energy is less, temperature will be less. Okay? So it's a mean of indirectly assessing the amount of thermal energy stored in a matter. That's kind of an indirect assessment tool. Temperature is that. Okay? It's measured in Kelvin or degree centigrade. We have heat transfer. Okay, whenever you have two bodies with different amount of thermal energies, okay, so one body has large thermal energy, one has smaller thermal energy. Okay, so the one which has large thermal energy will have large temperature, the one which have smaller thermal energy will have a small temperature, so there will be a temperature difference. So whenever you have temperature difference, then heat can transfer. So the amount of energy transferred is known as the heat transfer. Okay. Heat is the actual amount of energy transfer, and it is measured in joules or kilojoules. Okay. Heat rate, whenever we put the word rate with anything, so it means per unit time. So amount of heat transfer is joule or kilojoule, but heat rate will become joule or kilojoule per second, that means watt or kilowatt. It's clear? Heat rate. And then we have the heat flux. It's basically heat rate flux, but normally we call it heat flux. So flux means what? Rate was per unit time. Flux is per unit area. Something is passing through some area. So per unit area, how much it is passing. Okay? So it is heat rate per unit area. Heat rate was watt or kilowatt. So it's watt per meter square, unit of area is meter square. So it's watt per meter square or kilowatt per meter square. It's clear? So this is heat flux, heat rate, heat transfer, temperature, thermal energy. These are general terminologies, but you should be able to differentiate between them. What does they mean? Okay. Any question? Go ahead. Okay, this is we already covered as in the explanation. Okay, remember one thing. Suppose I have a fluid, I have a liquid or I have a gas which is moving from one place to another. Okay, and it's carrying energy with it. So you know it is convection when there is the bulk motion of the fluid. Okay. But don't you think when the fluid is moving from one place to another, it will have molecules which will interact with each other as well while they are moving? So interaction will keep on going within the molecules as well. They keep on colliding with each other. Okay? And that interaction means conduction is still going on there in it. So if there is convection heat transfer, it does not mean there is no conduction occurring within that fluid. Conduction is always occurring because always the molecules are colliding with each other. Is clear? Okay. Now for the heat transfer, we have to understand one thing, that for heat transfer, a must requirement is that there must be a temperature difference. Heat will always flow from high temperature to low temperature, but there must be a temperature difference. If there is no temperature difference, then the heat will not transfer. So that's a must need, that there should be a temperature difference. Okay. Both conduction and convection require the presence of temperature difference in a material medium. Okay, now there is one concept that you should know. Radiation is also a heat transfer phenomena, but it is slightly different from conduction and convection. For the conduction and for convection, we must need to have a temperature difference. But for the case of radiation, we must need to have a temperature only. Temperature difference is not important. Look, the thing is that any body in the universe, if it has a temperature above 0 Kelvin, it emits radiation. So any body in the universe, if it has a temperature above 0 Kelvin, it will emit radiation. Okay? However, the emission of radiation is a function of temperature. Larger the temperature of the body, larger will be the radiation emitted. Smaller the temperature of the body, smaller is the radiation emitted. So what happens is that if I have a body, it is emitting radiation as well as it is absorbing radiation at the same time. Okay? So if the body temperature remains constant, it means the amount of energy emitted is equals to the amount of energy absorbed. The body temperature drop if the amount of energy emitted is large, but the amount of energy absorbed is less. The body temperature rise if the amount of energy absorbed is more and the amount of energy emitted is less. You get the idea? So suppose if I have two bodies and both are at same temperature, there will not be any heat transfer between the two bodies, but that does not mean that there are no radiations emitted. Both the bodies are emitting radiation and absorbing radiations at the same time, but the amount of emission is equal to the amount of absorption. Okay? But although the temperature is same and the net radiation transfer is 0, but that does not mean that the radiations are not emitted. Radiations are still emitted, even if the temperatures are same. But the amount of emission is equal to the amount of absorption, so that there is no net heat transfer. Is it clear? So for the case of conduction and convection, we need to have a temperature difference. But for radiation, even if the temperature difference is not there, still radiations will be emitted. Is it clear?
Like a source.
Yes, like a source in the sink. Okay, this we already covered. Conduction is a theory, you go through it yourself. Okay, now let's come over to the main thing, conduction. How do we mathematically solve problems for conduction? Now the conduction phenomena is governed by a law which we know as Fourier's law. So Fourier's law is the law which govern the conduction phenomena. And according to Fourier law, Q double dash, okay, once again, we have Q is the energy, right? And Q dot is heat rate, okay? And Q double dash is heat rate flux or heat flux, okay? So Q double dash, according to the Fourier's law, is equals to negative K del T in the vector format, okay? Or Q double dash is basically equals to what? Q double dash is Q upon A. It's heat flux, right? Q double dash is Q upon A. So I can write that Q is equals to negative Ka, and this was written in the vector format. In the differential format, I can write here dt by dx. So you need to have a temperature gradient, a change in temperature between 2 points separated by a certain distance. So dt is the change in temperature, divided by dx is the distance across which the temperature change is there. Okay, area is, okay, what is this area? This is a cross section area. This is the area across which energy is being transferred. Okay, so if I have an area and energy is transferred perpendicular to that area, then that cross section area is A here. Now this A here will change based upon how the heat transfer is taking place. Suppose this is the body, okay? I have temperature 10 degree here and 20 degree here. So heat will be transferred from 20 to 10, okay? But what is the area across which heat is transferred? This is the area, right? So my A here will be this, okay? Suppose I have this surface 20, this surface 30. So heat will be transferred from 30 to 20, okay? Now my A is changed. Now my A is not this. Now my A is this, perpendicular to where the heat is being transferred. So based upon the direction of heat transfer, you will decide what will be A. A will change based upon the direction of heat transfer. Is it clear? So this is A. That's the temperature difference, which is a must. Then it should be separated by a certain distance. Okay, that's a dx. K is a material property. Okay, suppose I have suppose this is a steel bar, and I have 10 degree here, 20 degree here. Heat will be transferred. If I have, let's say, a brass material, again 10, 20 degree. If the temperature gradient is same, even the length is same, still the heat transfer capability will differ from material to material. Okay, that is the material property which is known as thermal conductivity K. Okay? So K is basically a material property. It is thermal conductivity and it is a material property. So it will not change if the material is not changed. But if you change the material, K will change. Is it clear? It's a constant, but it changes with material. It's a constant for the material. You change the material, K will change. If you do not change the material, K will not change.
Each material have its own K value.
Have its own K value. Is it clear? Okay, now can we derive the unit? Okay, now there is one important thing. It is written here in the differential format, so you have a negative sign here. Negative sign means if I have a body and the body has this surface 1, this surface 2, okay, and let's say the heat is transferred from 1 to 2, okay. So the temperature difference 2 minus 1 will be a negative value, okay. 1 minus 2 will be a negative value, okay. So temperature difference 1 minus 2 will be a negative value, okay. So final minus initial must be a negative. If you want the flow of heat to be in the forward direction, then the final temperature must be less than the initial temperature. Why? Because if the temperature gradient is not like that, heat will not flow in this direction. Is it clear? Yes, for it has to be high to low. Okay, so final minus initial must be a negative value. That's why you have a negative sign here. But suppose if you are just putting here the temperature difference, if you're just putting here a temperature difference, then you don't need to put the negative sign here, right? So I can write in the differential formula, it is written negative Ka dt by dx, but I can write here Q is equals to Ka delta T by delta x. Clear? Because this term it will give you a negative value, this negative will cancel with this negative and it will become positive. But if you are directly putting a delta x, delta T, then you don't need the negative here. Is it clear? Okay. Now what is the unit of this K? K is a material property. What will be the unit of K? You can drive the unit. Okay. So let's drive the unit for K. So Q is what? What's the unit of K? Q? Joule, right? This is Joule. Not Joule, consider it as Watt, because we are already always consider here as heat rate. Okay. So this is Watt. Okay. K unit we don't know. A is meter square. dt will be temperature, Celsius, Kelvin, okay, over meter, right? So what will be the unit for K? This meter will cancel with this. So it's watt per meter Kelvin, right? So unit of K will be watt per meter Kelvin. Is it clear? So that will be the unit of K. Watt per meter Kelvin. Is it clear or not? Is there anything which you do not understand? Please ask.
This one is called heat or heat flux.
This is heat rate. Heat rate. Okay. Heat flux will be Q double dash. If I put from this A from here to here, then this Q double dash will be heat flux. This is heat flux. Okay. So you have heat rate, heat flux. The two things that you should remember. Heat rate, heat flux. Okay. This is heat rate divided by area, heat flux. Any other question? Okay, so let's move ahead. Okay, so now we have a small numerical related to this formula that we have studied. Okay. The wall of an industrial furnace is constructed from 0.15 meter thick fire clay brick having a thermal conductivity of 1.7 watt per meter Kelvin. So you have a furnace and the wall of the furnace is made up of fire clay brick, right? And the thickness of this brick is given 0.15 meter, okay? And this brick is a material, for that material the value of thermal conductivity is given, okay? So K is 1.7 watt per meter Kelvin. So that's the K given, okay? And that's the thickness given, thickness of the wall given. Measurements made during steady state operation reveal temperatures of 1400 and 1150 Kelvin at the inner and outer surfaces. So you have the wall, and wall have an inner surface and an outer surface. So inner surface temperature is 1400 Kelvin and outer surface temperature is 1150 Kelvin. Okay. So temperatures of the inner and outer surface are given. What is the rate of heat loss through a wall that is 0.5 by 1 by 2 meter on a side? So the thing is that you have a wall, this is your wall. Okay, suppose if I make section of the wall, inside temperature is 1400 Kelvin, outside temperature is 1150 Kelvin, right? So since there is a temperature difference across the two sides of the wall, so heat will transfer. And this is a furnace, so heat will go out. So that heat going out of the wall is the loss of energy. Okay. So we need to find out what is the amount of loss of energy. The thickness of this wall is given. Thickness of the wall is 0.15, right? K value for the wall is given. We need to find out that how much is the heat loss. Okay, so we need to find Q. Okay, so Q is basically what? Q is equals to Ka delta T by delta X, right? Now, in this case, K is given. K is given. Delta T is known. Delta X will be what? The length across which heat is transferring. In this case, the length across which heat is transferring is the thickness, inner and outer surface. That is where the temperature difference is occurring. Okay, that's delta X. Okay, area is the cross section across which heat is being transferred. In this case, the cross section will be 1.2 times 0.5. Okay, so what is the rate of heat loss through a wall? That is 0.5 into 1.2 meter on a side. Okay, so now we know A, we know K, we know delta T, we know delta X. Substitute all the values, you will find Q. Is it clear? Delta X, look, delta X is always the thickness or the length across which heat is transferred. Now focus on my words. It is the length across which heat is transferred. In this wall, heat is transferred from inside to outside, so delta X become length, the thickness here. If the heat was transferred from this surface to this surface, then it would be W. From this surface to this surface, then it will be W. If it was transferred from the top to the bottom surface, yeah. So delta X depends upon what is the direction of heat transfer, in which direction heat is being transferred. Is it clear? In this case, it is the thickness. So now it's just a matter of substituting values. So substitute all the values and you get the answer. Is it clear or not?
Yeah.
Now there is one more concept that you should know. Sometimes we say one-dimensional heat transfer, sometimes we say two-dimensional heat transfer, sometimes we say three-dimensional heat transfer. What does that mean? Let me just elaborate you here this. Suppose I have this body and the temperature here is 20 degree and temperature here is 10 degree. This whole surface is 10 degree, this whole surface is 20 degree. Now you know in Cartesian coordinates how many axes we have? 3 axes, x, y, z. Suppose this is my x-axis, this is my y-axis, this is my z-axis, right? Now if this is 20 degree, this is 10 degree, do you think heat will be transferred in x-axis? There is no temperature difference, this whole 20 degree, right? Heat is not transferred in x-axis. Do you think heat is transferred in y-axis? Heat is not transferred in y-axis because the whole surface is 20 degree. But this is 20 and this is 10, so yes, heat will be transferred in the z-axis. So this is one-dimensional heat transfer, because in the other 2 dimensions, heat is not being transferred. Is it clear? Yeah, obviously area should be perpendicular, but what I am giving you right now, what I am trying to explain you is the concept between one-dimensional, 2-dimensional and 3-dimensional heat transfer. Okay? Now suppose, consider it that here the temperature is 20 degree, here the temperature is 10 degree, okay, but the top surface is at a temperature of say 5 degree, Okay. Now the thing is that we know that there will be heat transfer like this, but also there will be heat transfer in the y direction, because here the top now is 5 degree and this 20 degree, this 10 degree, but here top 5 degree, right? So now heat will be transferred in the y axis. There will be no transfer of heat in the x axis. Okay. There will be no transfer of heat in the x axis. Heat will be transferred in the y axis and in the z axis. So now it's a two-dimensional heat transfer. Now suppose I have here this 5 degree, this is 20 degree, this is 10 degree, and suppose this side is 30 degree. So now the heat will be transferred in all the directions. Okay. So that's a three-dimensional heat transfer. So basically what we do is that when we consider a one-dimensional heat transfer, we assume that the heat is not being transferred in the other directions, in the other two dimensions. So what would be the reason that heat is not transferred in the other two directions? Is because, like this example, we considered the wall, one side of the wall completely at 1150, other side of the wall completely at 1400. So now the heat will only be transferred from across the thickness, because across this length there is no temperature difference. Is it clear? So we are assuming that it is uniform. In reality, it's very hard to have a very uniform temperature distribution across the complete wall. Okay, but in order to simplify our problems, we make it one-dimensional. Your chapter 3 will be focused over one-dimensional conduction only, and you will find that one-dimensional conduction itself is so much complicated. Two-dimensional is almost impossible to solve analytically. Very little solutions are available, and we will move towards the numerical solution for two-dimensional, and three-dimensional are impossible. We have to move towards numerical solution. Okay. So that's the concept of one dimension, two dimension, three dimension heat transfer. We simplify our problems considering it one dimension. Obviously the answer will be a little wrong. There will be some error, but acceptable level error is okay. If the error is only 1%, less than 1%, okay. Okay. Is it clear so far? Okay. So time right now. Oh, I have time. So that's a solution. You see here, just okay, they solved it in 2 steps. They first find Q double dash, and then they said that Q double dash is equals to Q upon A, or Q is equals to Q double dash into A. You can solve it directly as well, no problem. Okay. Okay, now let's move towards the convection. Okay, for convection, this theory already I explained it to you. Convection is diffusion plus advection. I told you it's conduction, advection, but I said conduction is the same as diffusion. Okay, and this all theory already gone through. Boundary layer is too early to discuss here. It's something that you're going to study in chapter number 6 onward. So if I explain you this right now here, you won't be able to understand. So let's skip these. We have different kind of convections. We have forced convection, we have free convection. How these types of convection classify? Look, in convection we have bulk motion of the fluid. But how does this motion is created? How this motion is created? This defines that what kind of convection we have. If the motion is created externally by some external means, okay, so maybe you put a fan. Maybe if you have a liquid, you put a pump. So anything by external means, if you are putting up the motion, then this is forced convection. Any heat transfer because of that is a forced convection. Okay. However, if the motion is by natural means, okay, so you have fluid, you heat it, so the heated part of the fluid expands, its density drop, it moves up, and the colder one moves down. This is the buoyancy effect, and that's a natural phenomena. So if it is happening because of the natural phenomena, if the motion is happening because of the natural phenomena and that motion is responsible for the heat transfer to take place, then this is the free convection, natural convection. Okay. Anyways, this is something that you're going to study in detail. Chapter number 7 and 8 is about forced convection. Chapter number 9 is about free convection. Okay. So we're going to study that in detail there. That was just an introduction. We can also have mixed convection, which is a combination of force and free convection. We're also going to study that later. Okay, let's take a break of 5 minutes, and then we'll start again. Okay. So we started an introduction of conduction, and we solved a small numerical related to it. We studied the law of conduction, how mathematically it is represented, what each term means, okay, and how can we solve problem related to it. This is what we did for conduction, and we are now going to move forward for convection. Now, the law which defines convection is known as the law, Newton's law of cooling. Newton was, mashallah, a guy who worked in many areas. So it was not just the law of mechanics, not just the law of motion, first and second law of motion, but we will also have the Newton law of cooling here. Okay. So the Newton law of cooling is the law which defines so what is the law which defines convection? It is the Newton's law of cooling. So if I ask you in the exam which law defines convection, and if you write Newton's law, then I will deduct mark, because it is Newton's law of cooling. Newton has many laws. Okay. You have the laws of motion, first law, second law, third law. Okay. So if you just write Newton's law, I will deduct mark. It's Newton's law of cooling. And what does this law states? This law states that Q double dash is equals to, heat flux is equals to H multiplied by T S minus T infinity. So, or if I don't write in terms of the heat flux, so Q will be equals to HA multiply with the area, HA Ts minus T infinity. Now H is the heat transfer coefficient. Okay. Previously we had the thermal conductivity of the material, but now we have the heat transfer coefficient. Thermal conductivity was the material property. Now heat transfer coefficient is not the material property. It depends upon many things. We're going to study that in detail. In fact, your chapter number 7 till chapter number 11 is basically focused on finding this H. From chapter number 7 to chapter number 11, the whole material is just to find this H, because this H will be different for boiling, different for condensation, different if the fluid is moving inside a pipe, different if the fluid is moving over the pipe, different if you have a forced convection, different if you have a convection because of the boiling, because of the buoyancy effect. So this H will differ from case to case. Okay, and this H is basically the only thing because of which you have chapter number 7 till chapter number 11. Otherwise, this is the same law. This is the law which is used. But only finding this H is the main thing. So this is chapter number 1, introduction. So H will be given to you in the problem. But in future, when you move to those chapters, then you will have to first find these H's. And then you apply this thing. Okay? So it's a convective heat transfer coefficient. It's a convective heat transfer coefficient. Okay, convection heat transfer coefficient. What is the unit? You can drive the unit. Drive the unit, please. What's the unit of H? So Q will be watt, A will be meter square, Ts minus T infinity. Ts will be the surface temperature and T infinity will be the fluid temperature. Okay, this is Kelvin. Okay, so this is Kelvin, this is meter square, this is watt. So unit of H will be watt per meter square Kelvin. So you see there is a difference between the unit of H and the unit of K. What's the difference? Meter square. Here it was just meter, here it is meter square. Is it clear? So this is the Newton's law of cooling. Okay. Typical values are provided here for heat transfer coefficient. For free convection, the values are normally between 2 to 25 or 50 to 1000. Forced convection 225 to 250, 10,000 to 20,000 for liquids. Convection with phase change, very high values. These are not the things for you to remember, just as a reference. Okay. Sometimes it's good if you know the reference. For example, if I say that the distance from this building to our engineering building is 10 centimeter, would you agree that? It's not 10 centimeter obviously, because you know the reference, so it's that much far. Okay, so if I say that the distance from Saudi Arabia to US is 50 kilometers, it's not agreeable. Okay, because you know the reference. So sometimes it's good that you know that, okay, the values should be between this range. Okay, that's why it's given. Okay, radiation. For the case of radiation, it is defined by the law known as Stephen-Boltzmann law. Stephen-Boltzmann law. Okay, this is Stephen. Boltzmann law. So you had the Fourier's law, then you have the Newton's law of cooling, and for the radiation it is known as, it is defined by Stephen-Boltzmann law. Okay. Now how do we define that is that we know that every object is emitting radiation as well as absorbing radiation. Okay. So you're going to study that in a bit more detail in chapter number 12 and 13, but just giving you a gist is that we define an ideal body. An ideal body which emits maximum amount of radiation and which absorbs the maximum possible radiation. Okay, and we call it as black body. Okay, so radiations emitted by black body or energy emitted by black body is basically sigma T raised to the power 4. Okay, how do we come up with this formula? When you go to chapter number 12, 13, you will understand that. Okay. But it is sigma. Sigma is basically a Stephen-Boltzmann constant. It has a fixed value, and that value is 5.67 into 10 to the power minus. Sorry, it's written wrong here. Minus 8. 5.67 10 to the power minus 8 watt per meter square Kelvin power 4. Okay. So this is the value of sigma. It's fixed value. Obviously, it will be provided to you in the book of tables. Book of formulas. We have a book of formulas, 44 pages. No, we have different appendices tables as well. Along with that, we have the book of formulas.
60 pages.
So this will be provided to you in the exams. So anyways, the value is here. This 5.67 10 to the power minus 8, it will be provided to you in the book of formulas. And this is a Stephen-Boltzmann constant multiplied by the temperature, power 4, whatever the temperature of that black body is. Okay. However, the real bodies are not the black bodies. So black body is an ideal body, it will emit maximum possible. But real bodies will emit less than ideal. Okay. So we define emissivity, it is like a percentage. is it emitting 90% of the ideal body, 80% of the ideal body, 70% of the ideal body. So we define it by emissivity. Okay. So real body is an amount of energy emitted by real body is emissivity multiplied by the amount of energy emitted by the black body. Okay. So this is equals to epsilon sigma T power 4. Okay. So that was the energy emitted by the ideal body multiplied by the emissivity. It's like the efficiency or percentage. It will never be 1. It will be less than 1. Okay. So that's the emission. Okay. So that was about the emission. But what about the absorbance? Any body emit, but at the same time it also absorb. But absorption comes from the surrounding. Depends upon the temperature of the surrounding. The surrounding is emitting, that will be absorbed. Right? So for the absorption, we define it as irradiation, and given as G. So G is equals to, again it depends upon the emission of the surrounding. So if the emission of the surrounding is sigma T surrounding power 4, okay, and then you define absorptivity. Ideal body absorb everything, but an actual body cannot absorb everything. Okay, so it will have an absorptivity alpha. Okay, and the amount of heat transfer will be the difference between emission and absorption. Amount of heat transfer Q will be emission minus absorption. So if large emit, less absorb, so Q will be net out. If large absorb, less emit, then Q will be net in. Right? It's like this. So Q in this case will be E minus G. Right? And normally for any body, its emissivity and absorptivity are same. How much it can emit is equals to how much it can absorb. Okay? If the emissivity and absorptivity of a body was not same, then its temperature will keep on changing. It is because this body, for example, this body, it is whatever the temperature it is, its temperature is not changing. If I put a thermometer on it, it will give some temperature, and after 15 minutes, if I again put the thermometer, it will give the same temperature. So the temperature of the body is not changing because its emission and absorption are same, right? And that is because its emissivity and absorptivity are same. Okay. So anyways, so I can replace this alpha with epsilon as well because they are equal. Okay. So it will be what? It will be epsilon sigma T power 4 minus again epsilon sigma T surrounding power 4. So I can write here epsilon sigma T power 4 minus T surrounding power 4. This is Q. Right? Emissivity multiplied by the constant multiplied by T of that object power 4 minus T of the surrounding power 4. I told you that it was supposed to be here, but I substituted alpha with epsilon because they are same. Yeah. Is it clear? So this becomes the main formula for radiation. But if you see here in this formula, temperature are power to the power 4. So for other formulas, even if you put temperature in degree centigrade, not a big issue. But for this formula, if you put temperature in degree centigrade, a big problem, a big blunder, because your answer will go horribly wrong. Because here the temperatures are power 4. You must put temperature in Kelvin. For others, it's not an issue because suppose the temperature is Ts is Ts is 17 degree, 17 plus 273 minus T infinity is 10 degree, let's say, minus 10 minus 273. 273 will cancel. In this case, it cannot cancel because there is power. Is it clear? So here, if you just put even in degree centigrade, not a big issue. Here, if you put in degree centigrade, a big issue. Okay. So make sure that you don't make mistake in the units. Okay, I can write the formula for radiation in the same format as here. I can write, okay, there is, sorry, one problem. It is Q double dash here. So that's Q double dash. If I want to remove the Q double dash from here, I have to put area here, right? Now I can write the same this formula similar to this. Okay, how? In this formula you have A, so A is here. You have Ts minus T infinity. Here we have T power 4 minus T surrounding power 4. But I can split it. Yeah, in the multiplication format. If you have A power 4 minus B power 4, I can write it as A square minus B square into A square plus B square, right? And then A square minus B square I can write as A minus B into A plus B, A square plus B square, right? So here A minus B will be here, like here we have Ts minus T infinity. And all other terms will be there as well. Okay? So I can write here Q is equal to, you can see here, huh? Q is equals to A epsilon sigma T minus T surrounding into Ts plus T surrounding into Ts square plus T surrounding square, right? I have done this thing. Okay, so now we have A here, like A here. We have Ts minus T infinity, we have Ts minus T surrounding. And then we had H. So we put all things together in H, the remaining things. Okay, and we call it HR because this is the H for radiation, right? So what are the things that will go in HR? Epsilon will go in HR, sigma will go in HR, Ts plus T surrounding will go in HR, Ts square plus T surrounding square will go. 4 things will go in HR, right? So it becomes Q is equals to HR, HRA Ts minus T surrounding. Is it clear? Just this is mathematical manipulation. I want to write this thing in a similar format as this thing. So that was convective heat transfer coefficient. Now this is not convection, this is radiative heat transfer coefficient. Okay, that was convective. This is not convective HR, this is radiative heat transfer coefficient. Is it clear? Still okay, khalas. Here you can use degree, but within HR you cannot because you have a square value. It's better to use Kelvin in any case.
Also, if I needed to use this new formula, it's not needed to prove it.
No, you don't need to prove it. You use directly.
So from here we can get HR.
Yes, you can get HR. Yeah. For finding HR, we will see in chapter 12, 13. Is there anything that you don't understand?
This AB, what does it mean?
It's a black body emission. We say that a black body is a perfect body. And how much it emits? It's sigma into T raised to the power 4. How do we get this formula? We'll study in chapter 12, 13. Right now here there's an introduction just. So here you studied 3-4 many important things. First of all, what are the modes of heat transfer? What does their physical significance? What does they physically mean? Which laws are governed by or explains the mode of heat transfer, then how do we represent them mathematically? What does each and every term mathematically means? We studied all these things. We studied all these things here right now in the introduction. So this chapter is known as introduction chapter, but it is not introduction actually. It is one of the most important chapter because you have studied the basics here. Now in the future chapters, as I told you, from chapter number 6 to chapter number 11, this formula is not going to change. You are going to apply this formula, but all the time this H is something that you will have to see. Okay. So this chapter was actually not kind of, it was introduction, but it was the basis. Okay. Do you understand these formulations and everything written on the board? If there is anything that you don't understand, please ask.
In the first three formulas, we have E and we have G.
Yeah.
E is for
Emission. G is for absorption, something coming, irradiation. We call it irradiation, something incident coming onto the body.
Just one body.
Yes, one body. Okay. There is a lot of theory written here, but what are the things that we focused here on in my lecture? Just focus on that. These theories we are going to study again in detail in their respective chapters, and wherever they will be important, I will emphasize, I will focus that okay, these are the areas that you should focus for your exams point of view. But here general understanding and the things that we studied, discussed in the class are important. Okay. So we get this HR is equals to this formula. Same thing, we derive this. So Q radiation will be this. Okay. Let's have this example, and that's it. After this example, our today's lecture is over. Okay. An uninsulated. What does insulation means?
No,
And uninsulated means?
There is transfer.
Yeah, there will be heat transfer. Okay, so nothing is restricting the heat transfer. An uninsulated steam pipe. So we have a pipe which carries a steam, passes through a room in which the air and walls are at 25 degrees centigrade. So suppose you have a pipe which is passing through this room. Okay, the walls are at 25 degree, the room is at 25 degree. Okay, and we have a pipe which is passing through this room. Okay, the outside diameter of the pipe is 70 millimeter. Okay, so we have the pipe, and the pipe has diameter, outside diameter 70 millimeter, right? And its surface temperature and emissivity are 200 degrees centigrade and 0.8. So surface temperature, the surface of it, Ts, is at 200 degrees centigrade, and its emissivity is 0.8. Okay, emissivity is 0.8, surface temperature 200 degrees centigrade. Outside temperature was already given, air and walls. Okay, air means obviously there will be some convection heat transfer, so the T infinity will be 25 degrees centigrade, and surrounding walls, they are also, so T surrounding is also 25 degrees centigrade, right? Because the air and walls both are at 25 degrees centigrade. What are the surface emissive power and irradiation? First thing is asked, what is the surface emissive power and irradiation? So first thing is asked, what is surface emissive power is E. So what is E? Okay, and irradiation is G. First is asked, what is E and what is G? Okay, so E will be what? E will be epsilon sigma T power 4, right? Epsilon is given emissivity 0.8, sigma is a constant, 5.67 times power minus 8, and temperature is given of the surface. But will you take the temperature 200 degrees centigrade? Change it to Kelvin, right? So you will get what is E. Is it clear how to find E? What is irradiation? Irradiation is alpha G is sigma. Okay, you have to understand one thing. One thing is how much is the amount of energy incident coming, then how much is the amount of energy absorbed. There are two different things. Suppose 100% energy is coming, but not necessarily all 100% absorbed, 80% absorbed. So this absorptivity, when we use this G, so that depends upon how much energy is absorbed. But irradiation is without alpha. Alpha is the absorptivity. 100% was coming, alpha let's say is 0.8, that means 80% absorbed. Okay, but if we don't want to know how much is absorbed, if we just want to know how much is the incoming, then alpha is not needed, then it's just sigma T surrounding power 4.
It's not mentioned in that question, so we don't use it.
No, it's mentioned what is the surface emissive power and irradiation. Okay, it is not mentioned, it is not asked that determine the amount of energy absorbed by the body. It is said what is irradiation. Irradiation means how much is the incoming radiation. It's not said how much it's absorbed. Okay, so if it is said how much absorbed, then you have to use alpha. But since it is said what is the irradiation, irradiation is sigma T surrounding power 4. Is it clear? So we know what is sigma, we know T surrounding power 4, so that will give you G. Irradiation means, okay, this is the body, it is emitting radiation. Irradiation is how much is the incoming radiation on it.
So this is the IR.
IR irradiation, right. Okay, but how much is the absorbed?
Yeah, I know, but I want to ask the vocabulary.
Vocabulary, irradiation, yes. Is it clear? So we can find what is the emissive power, we can find what is irradiation. E and G. Done? Anything which is not clear in it. But remember here, both need temperatures. And temperature must be in Kelvin. If you put the temperature in degree centigrade, big mistake. Okay. If the coefficient associated with free convection, so they are saying if we have a coefficient means H. But H related to what? H associated with free convection. I mean it's convection. Heat transfer from the surface to the air is 15 watt per meter square Kelvin. This is not Q. You look the unit. Okay, watt per meter square Kelvin. So we are given what? H, but convection H. So we are given this H, right? What is the rate of heat loss from the surface per unit length of the pipe? Now the thing is that you have a pipe. Let's say this is the room and the pipe is going through the room. Now the pipe is uninsulated, so there will be heat loss. The pipe is very heated, 200 degrees centigrade. The room is 25 degrees centigrade. So obviously heat will be transferred from the pipe to the room. But what are the two ways of heat transfer through which heat will be transferred? What are the modes here? It will be convection plus radiation. Heat will be lost from the pipe to the room by two modes, convection plus radiation, right? Why not conduction? Yeah, because we are not considering the end losses. We are just considering what is heat being transferred to the room, okay? And the pipe is in air, okay? So it will be by convection and by radiation. So the total amount of heat transfer will be what? So Q total will be Q convection plus Q radiation, right? That will be the total heat transfer. Okay. Or I can say that Q convection is equals to H A T S minus T infinity, right? Plus Q radiation is equals to H R A T S minus T surrounding. Is it okay?
Yeah.
Is it clear? Now here, do we know this H?
Yes.
For convection
Yeah, it's given very good.
is given, right? Do we know Ts? Ts is surface temperature. Surface temperature of the pipe. We know, right? So we know Ts, we know Ts. Do we know T infinity? Not the walls. Here for convection, it should be the air temperature. For convection, it should be the air temperature. And it is given. The air and walls are 25 degree. So T infinity is known. What about T surrounding? 25. Why? Because it's the walls. It's 25, known. Wall. Okay. So T surrounding is known, Ts is known, T infinity is known, Ts is known, H is known. Right? What about HR? So for HR, you know the formula is HR is equals to epsilon sigma Ts plus T surrounding into Ts square plus T surrounding square, right? This is the formula for epsilon sigma Ts plus T surrounding Ts square plus T surrounding square, right? You're still processing this in your mind.
No. Okay, it's okay.
No problem. I give you time. Process it.
Still this is sigma. I think it's not good.
Sigma is constant. Its value known.
Then everything
Is it okay?
Yeah.
Okay. So now epsilon is given for the pipe. Emissivity is given. Sigma is a constant. Ts known, T surrounding known, Ts known, T surrounding known. HR is known. Okay. What about A? Now use your mind. You have a pipe. Pipe is losing heat. So what should be the area? What is the area across which heat is being lost? Surface area of the pipe. Now complete pipe, what will be the surface area? What will be the formula? Don't tell the formula of cross section area. Surface area of the pipe. So this is the pipe, so that's the complete surface from which heat is being lost. L times d pi. Pi d is the circumference multiplied by the length. Pi dl. Pi dl is the surface area, right? Pi dl is the surface area. So instead of A, let me write here pi dl, okay? Pi dl. Also instead of A, I will write here pi dl. Can you see it? Okay. I have written pi dl here. I have written pi dl here. Diameter is given or not? 70 millimeter, right? Diameter is given. Pi is a constant. So pi d. L is given or not? No, look here. What is the rate of heat loss from the surface per unit length of pipe? No need to find L. We do not need Q. We need Q by L. We do not need Q. We need heat loss per unit length of pipe. So we need Q over L. So divide by L, L will cancel. Divide by L, L will cancel. Okay? So now everything is known. Just substitute the values, find out how much is the heat loss.
Here, the law says Q is equal Ts negative minus T surrounding. So why here put the positive?
I put here negative.
This is
No,
HR.
put HR.
No, for HR, I did not say Ts minus T surrounding. Look, we said here Q is equals to this whole term. But then we say that I need to write this in this format.
Yes, HR.
In this format, right? So in this format, A is here, Ts minus T infinity is Ts minus T surrounding here, and the other things I said will go in HR. So in HR there is no minus. In HR you have epsilon, you have sigma, you have Ts plus T surrounding, Ts square plus T surrounding square. So there is no minus in HR. Hmm? Pi dl. Surface area is pi dl for the pipe. Okay, class, it's done actually. If you see here, we first found E, then we found G, as I said, okay, and after that this is Q is equals to H A Ts minus T infinity, and this is for radiation. Substitute the values, we get the answer. That's it. Class, we're done till here. That's it. So today's lecture is over now. Okay, so we'll inshallah continue with this. Chapter 1 is not complete yet. We are going to inshallah continue with this tomorrow, and we will complete chapter number 1 inshallah. Anybody has any question? Yes. Yes, he asked, look, what are the surface emission power and irradiation? That's all. Okay? Okay. Khalas.